Namaste everyone, welcome to CET NEET classes, physics classes. So in the previous class we have seen the tangent galvanometer and vibration magnetometer. We went a little bit out of the syllabus, but formulas were not out of the syllabus. Some ideas and concepts in which you have to apply the already learned formula. That is little different, that's all. Right? So namaste. So today we will see deflection magnetometer. What is deflection magnetometer? Again same principle. It's just a differently designed instrument to find out the strength of the magnetic field or maybe the magnetic moment, current, anything if you want to find it out. And we use a bar magnet, and we will recall whatever we have studied in the previous class. One is the magnetic field due to a bar magnet. You know that a magnet will have its own dipole moment, and if its dipole moment is m, right, and can be also written as the pole strength qm into the length L, and if L is 2L, okay, the length 2L, as if you multiply, as if you find out the dipole moment of an electric dipole, which says it is the product of one of the charge and perpendicular distance between the charges. Here it is the product of one of the pole strength and the distance between the two poles. Okay, if you take a dipole like this, then on the equatorial line, the electric field at a distance d is B is equal to mu naught by 4 pi m by d cube. And over the axial line at any point, the magnetic field B is equal to mu naught by 4 pi 2m by d cube. Here it is double. Whereas in the case of electric field, electric dipole, electric field at any point on the axial line, equatorial line is 1 by 4 pi epsilon naught p by d cube, where p is 2a into q. Whereas here it is mu naught by 4 pi into 2m by d cube. So here it is 1 by 4 pi epsilon naught 2p by r cube. Here 1 by 4 pi epsilon naught p by r cube. So that is a magnetic field. And what is the principle of the tangent galvanometer? Already you have a magnetic field, say Earth's magnetic field, freely available everywhere. We can use it anywhere. And if you place a small magnetic needle, it stands in that direction, because the force, Earth's magnetic field forces it to stand like this, so it will oscillate like this, and finally it will come to rest in this direction. Now take a coil, apply a magnetic field in this direction. The coil will always produce a magnetic field along its axis. So plane of the coil should be along the magnetic field, and the magnetic field produced by the coil will be perpendicular to this. So this is magnetic field due to the coil. And because of this needle, which was standing like this, now turns by an angle theta, like this. Okay, it turns by an angle theta, and this is theta. And if you want to know, then the new magnetic field is equal to old magnetic field into tan theta. This is what we write. Okay, now how is deflection galvanometer or deflection magnetometer? It is very simple. Of course, vibration magnetometer, you know, if a magnet is made to vibrate in a magnetic field, then the period of oscillation is given by 2 pi into square root of moment of inertia divided by magnetic moment into magnetic field, MB. So that we have applied. How do you cut a magnet into two pieces along length and along perpendicular to the breadth? So all those things were studied, and I think you have followed it, because something was missing, and I have given you PDF which contains the solutions also, because when I was dealing with that, it was raining very heavily, and I don't know whether it looked like I was doing class at night, right? But you might have followed it. Okay, now what is deflection magnetometer? Very simple. There are two positions in the deflection magnetometer. It has a long wooden box, a wooden board. Over the wooden board, there is a compass, and there is a small magnetic needle in the compass. Suppose the magnetic needle is standing like this, say. What does it mean? Say this is the north pole of the needle, because I will take some time to explain this, but once you follow the explanations, it becomes easier. That's why I take some time to explain this. So a magnetic needle is kept like this, okay? Now, the meaning of this is Earth's magnetic field is like this, right? It is BH. Say BH is like this. Now, I take a magnet and I keep the magnet like this, north, south. Now the needle is under confusion, because earlier the needle was standing in the direction of the Earth's magnetic field, because that was the only, Earth's magnetic field was the only magnetic field which was directing the needle to stand somewhere, right? So in this direction, somewhere means. Now came another magnet which produced another magnetic field. And how is the magnetic field lines outside a bar magnet? It starts from north and ends in south, you know it. Inside the magnet it is south to north. So if the magnetic field lines start from north and end in south like this, how is the magnetic field line here? There is one more magnetic field produced because of this bar magnet like this. So this is a magnetic field due to the bar magnet, B bar I will write. Now because of these two magnetic field, what will happen to the needle? Needle will turn by an angle theta. It will stand in the resultant direction. And you know that if two vectors are acting in the two sides of a rectangle, resultant is given by the diagonal. So it will stand somewhere here like this, right? It will stand like this. So that is the direction of the resultant magnetic field, okay? So this is resultant. So it will turn by an angle theta. Again apply the same tangent law. So we have used already existing Earth's magnetic field in one direction. We have applied another magnetic field which is perpendicular to that using a bar magnet, and this position is called tan A position, okay? Tan A position means the second magnetic field which has to be applied if you want to apply tangent law, that is always used as the axial line of a dipole magnet, bar magnet. See, what is the new magnetic field used? Already there was existing some Earth's magnetic field. The new magnetic field used was along the axial line of this dipole, bar magnet. So if axial line magnetic field is used, it is called tan A position. This is called tan A position. Okay, what is the new magnetic field? Now this is BH, and this is the magnetic field due to the bar magnet, and that means this one. So this is also BH because the length of this and length of this are same. If this is the magnetic field due to the bar magnet, this is also B bar. Now take tan theta. Or you can write new magnetic field is equal to old magnetic field into tan theta. That is also possible. Or new magnetic field, opposite side, that is this one, by adjacent side, this one, BH. Now what is B due to bar magnet? B due to bar magnet is the magnetic field produced by this bar magnet from its center up to this distance. Suppose this distance is D. If the needle is kept at a distance which is equal to D from the center of this bar magnet, then you have to find out the magnetic field due to the bar magnet along the axial line. So that is equal to mu naught by 4 pi 2m by d cube, if this distance is D, divided by B due to what is this, H, right? So we have different sounds coming from different places. Sometimes crow will be crying somewhere, and sometimes this railway sound, and sometimes rain sound. So classes are becoming so natural, right? Please bear with all those things. So this is what you have to do, and you have to adjust this, and finally you have to get some answer. So looks a little bit out of syllabus, but not out of syllabus, it is within the syllabus. This is tan A position. What do you mean by tan B position? I'll write here. Tan B position means you have to use the magnetic field of the bar magnet along the equatorial line, that's all. So I will keep the whole wooden block like this, and let the compass be kept such that the magnetic needle stands like this. What do you mean by this? The magnetic field due to the earth is like this, BH. Otherwise the needle wouldn't have stood like this. It is standing like this, and that's why the magnetic field is like this. Okay. Now how will you keep the bar magnet, sir? Bar magnet is kept somewhere here like this. This is because I want to use the magnetic field produced by the bar magnet along the equatorial line. That is tan B position. Here it is on the axial line. So if this is so, then how is the magnetic field? Suppose this is north and this is south. Then the north pole, from the north pole towards south pole, magnetic field lines, right? So here it is like this. So magnetic field due to the bar magnet is like this, B due to bar magnet, and these two will produce a resultant here. This needle will turn by an angle theta like this. Now again tan theta, shall I write it directly? Opposite side, this one, this is B due to bar magnet. BH is this one, right? This is BH and this is B due to bar magnet divided by BH. adjacent side BH. And what is B due to bar magnet? It is on the equatorial line. Suppose this distance is D, that is distance from the needle to the center of the magnet is D. What is the magnetic field due to a bar magnet on the equatorial line? B is mu naught by 4 pi m by d cube, not 2m by d cube, by BH. That's how you have to solve this. So very simple problem, right? Once you understand this, you can do that. So you have to apply tangent law. That means there should be an original magnetic field. Simply you can remember it like this. And you have to produce another magnetic field perpendicular to that. If it is done using a coil, then it is called tangent galvanometer. Yesterday I have seen tangent galvanometer. I have it here, right, in the previous class, right? So this is a tangent galvanometer where you have a compass needle here and it makes the needle stand like this, Earth's magnetic field, and there is a coil. Coil shouldn't be placed like this because the axis of the coil lies here. It should be like this. Plane of the coil should be along the Earth's magnetic field, so that magnetic field produced by the coil is perpendicular. So this is one method, that is tangent galvanometer. Whereas here we are using a bar magnet. If the axial line of the bar magnet is used, then it is tan A position. If the equatorial line of the bar magnet is used, it is called tan B position. Okay, shall we move on to the problems now? We will use 2 or 3 problems so that we will get the idea very clearly. Okay, this is the first problem. So you keep that PDF questions with you, because otherwise you can't see the options sometimes. If it is in equation form, it becomes difficult to enlarge it and paint it and all. So better you use that PDF also. Yeah, a short magnet produces a deflection of 37 degrees in a deflection magnetometer in tan A position. That means you are using axial line of the dipole. At a separation of 10 centimeter from the needle. The ratio of the magnetic moment of the magnet to the Earth's magnetic field is, so you have to find out magnetic moment M divided by the Earth's magnetic field BH. That ratio you have to find out, right? So what is the tan A position? You have a magnetic needle here, right? Magnetic needle is standing like this and the Earth's magnetic field is like this, say. And the bar magnet is used such that it produces magnet along its axial line, and this is the magnetic field due to the bar magnet. So any needle which was standing like this, as soon as the magnet is brought, it turns like this and it produces a deflection, and this is the deflection from here towards the other direction, theta. So what is tan theta? It is the new magnetic field produced by the bar magnet divided by old magnetic field BH. What is the magnetic field produced by the bar magnet? It is on the axial line, mu naught by 4 pi 2m magnetic moment by this distance, say I'll write it as d 2m by d cube, right? Yeah, right, into 1 by BH. So they have asked you to find out m by BH, the ratio of magnetic moment of the magnet to the Earth's magnetic field. This ratio itself you have to find out, and you know that this is 10 to the power minus 7, because mu naught is 4 pi into 10 to the power minus 7. By 4 pi gets cancelled. So I will bring it here, tan theta, and it is given tan 37 is 3 by 4. We will substitute it once. 3 by 4 is equal to 10 to the power minus 7, 2 times m by bh. D cube remaining. What is d cube? And it is at a distance of 10 centimeter. 10 centimeter means 10 into 10 to the power minus 2, that is 10 to the power minus 1. Whole cube, 10 to the power minus 3. D cube. So m by bh you keep it here, remaining things you bring it here. So what is the answer? It is 3 by 4 into 2 here, this 2, 10 to the power minus 3 to the numerator, 10 to the power minus 7 to the denominator, 2 have brought, that is equal to m by bh. M by bh, yes. Now 3 by 8, 10 to the power plus 7, 4. So 3 by 8 into 10 to the power 4. Do you have, yes, this is the answer. You can check it in your PDF because this appears very small. 3 by 8 times 10 to the power 4. That is the answer. So very easy. Just you have to remember the theory, not the by-hearting formula and the way in which you align it and all these things. It is very difficult. So you just know the theory behind it, right? Shall we move on to the next question? 52. Yeah. A magnetometer is used in tan B position. That means equatorial line magnetic field. Tan B position. Deflection of the needle is 37 degree. Find the distance of the magnet. Of course, tan 37 is not given here. It is 3/4. Find the distance if, something is missing. If m/bh, that should have been given there. It is not given, right? It should be given. m/bh is equal to if m/bh, that previous problem, from the previous problem here, m/bh is equal to 3/8 into 10 to the power 4. That was the answer, right? Last problem answer. Yes, m/bh is equal, no, that is the next one. 3/8 into 10 to the power 4. 3/8 into 10 to the power 4. Yes, that is the data. If that is missing, okay. Here, yes, that you have to take it. If m/bh is equal to 3/8 into 10 to the power 4, what is the answer? What is the distance? That is the question, right? This should be given. If m/bh is equal to 3/8 into 10 to the power 4. Okay, so it is the reverse of the previous problem, but position is different. Not tan A, it is tan B. That means how do you have to place it? The whole wooden board should be like this, and the compass should be here, and the needle should be like this, and magnetic field should be vertically up. Earth's magnetic field is BH like this, and you have to place the magnet like this, north south. Okay, at least if you work out problems of this type, some direct problems become easier. Suppose all these things are directly given in the problem, magnet is kept like this and like that, then it becomes easier. Okay, the north to south magnetic field is like this, from north to south, so the magnetic field due to the bar magnet is like this. And once this is also applied, the needle stands in this direction, okay, resultant direction. This is the angle through which the needle will turn after this is brought. Okay, what is tan theta? Opposite side, that is magnetic field due to the bar magnet divided by BH. Only the thing is, formula remains the same. Tan theta is equal to B due to the bar magnet by BH. If it is tan A position, this bar is 2m by d cube. If it is tan B position, m by d cube, that's all. Okay, tan theta, tan 37. Now it is tan B position. That means you have to go for equatorial line. B bar due to bar magnet, mu0 by 4 pi. M by d cube. That means this is d, the distance at which the bar magnet is kept from the center. M by d cube into 1 by bh. But m by bh is given 3/8 into 10 to the power 4. Now it is not 2. Tan 37 is, you have to take it from the previous one again, 3/4. 3/4 is equal to mu0 by 4 pi 10 to the power minus 7. You need not remember this. For CET it will not be given like tan 37 or so. Even if it is given, the values will be given. But for JE and all, you have to remember it. 3/4 10 to the power minus 7, mu0 by 4 pi 1 by d cube. D cube is the thing which I want to find out, because they are asking you the distance, m by d cube. M by bh. M by bh is already given 3/8. 3/8 into 10 to the power 4. Correct? 3 gets cancelled, and d cube I will bring 4 here, d cube here. So that implies d cube is equal to 4 here, 4 into 10 to the power minus 3 divided by 8. Am I right? 4 into 10 to the power minus 3 divided by 8, and it becomes 1 by 2. That is equal to 0.5 into 10 to the power minus 3. And cube root, if you want d, is equal to 0.5 into 10 to the power minus 3. It's cube root, and it should be 5 into 10 to the power minus 4. There is no 0.5 into 10 to the power minus 4 is wrong. 15 to 10 to the, yes, this is the answer. 5 into 10 to the power minus 4. That is the answer. You can't see this clearly, but you can get it from the PDF. It is 5 into 10 to the power minus 4 to the power 1 by 3. Cube root of 5 into 10 to the power minus 4. Okay, we will move on to the next question. 53. A deflection magnetometer is placed with its arms in north-south direction. Okay. Then That means the magnetic needle should be parallel to the this one. It should be parallel. North-south direction means it should be parallel. So I'll keep it as it is. In a deflection magnetometer, the whole apparatus is kept such that the needle stands in the north-south direction. In the same direction, the magnetometer is kept. Magnetometer means this whole wooden box, right? So it is kept in the magnetic field direction, BH. Then, how and where should a short magnet be placed so that the needle can stay in any position? You have to understand that last sentence. How and where should a bar magnet be placed? Having M by BH is equal to 40 ampere meter square. It is given M by BH is equal to 40 ampere meter square per Tesla. Where should you place that magnet with this ratio of magnetic moment per Earth's magnetic field? Be placed so that needle can stay in any position. What do you mean by needle can stay in any position? Any freely suspended magnet is not free to stay anywhere. It stands in the north-south direction. Why? Because Earth's magnetic field is in the north-south direction. If a magnet is staying in any position means there is no other field, right? There should not be any magnetic field, or the needle should be free from any external magnetic field so that it is free to rotate in any position. For example, if you take a wooden stick and suspend it, it is free to rotate in any position. It's free to stand in any position because it is not affected by magnetic field. It is affected by only gravitational field. Gravitational field is vertically downward, so it can rotate anywhere like this. Similarly, this magnet should be free from any magnetic field, but there is Earth's magnetic field, sir. Cancel it by applying another equal and opposite magnetic field like this. So how to apply an equal and opposite magnetic field like this? You have to take a bar magnet now, right? You have to take a bar magnet such that its magnetic field should exist like this, isn't it? From north to south like this. So will you have the magnetic field like this due to a bar magnet with its south pole near the magnet? If you place it like this, then what happens is this magnetic field can be cancelled on the other side. So if BH is like this, it should be cancelled by the magnetic field like this. So let this distance towards the center of the bar magnet be d. Now the equation which I have to apply, no tan theta, nothing. This, you ask this needle now whether you are rotating in any magnetic field. Sir, I am rotating in two equal and opposite magnetic fields, so net magnetic field is 0, so I am free, sir. I can stand anywhere now. So if it is so, then B due to bar magnet must be equal to B due to Earth's magnetic field. B due to bar magnet is on the axial line, right? So that means mu naught by 4 pi 2m by d cube must be equal to the magnetic field of the Earth, horizontal component of Earth's magnetic field, and m by bh is given, so let us use it. They are asking you at what distance, and south pole should be kept, that we know that. D cube is equal to mu naught by 4 pi 2m by bh. So substitute this, 10 to the power minus 7 into 2 into magnetic moment by bh, that is given 40, that is completely given, is equal to d cube. This is 80 into 10 to the power minus 7, 10 to the power minus 6 if I write, it is 8. 1 0 you donate it to this one, 10 to the power minus 6. 8 into 10 to the power minus 6 d cube. What does it mean? D is equal to cube root of this, 10 to the power minus 2, and cube root of 8 is 2. 2 into 10 to the power minus 2. So a south pole must be kept because the magnetic field should be like this, so as to cancel BH. So at a distance of 2 centimeter with north pole pointing towards south. North pole pointing towards south. So Earth's magnetic field is from in this direction, and a north pole pointing, that is not the answer. At a distance, north pole pointing towards south, as it becomes correct, right? At a distance of 8 centimeter, wrong. At a distance of 2 centimeter with south pole pointing towards south. South pole pointing towards south, no, not right. So it should be this one. A north pole pointing towards south is correct, right? The needle stands like this, it shows north, right? BH always shows north, because any magnetic field, when a magnetic needle is kept in a magnetic field, the pointer, that is north pole of the magnetic field, will show the north. So if this is north, then north pole of the needle should be kept towards south, and south should be kept towards north. Yes, this becomes correct, right? So this is north and this is south. So towards south you should have north, here it should be south. At a distance of 2 centimeter, north pole pointing towards south, you have to keep the magnetic bar magnet. So that's how. And this is a reference for us to see the direction, because magnetic needle is standing like this, so it is pointing towards north. And the remaining, of course, this is south. So now north should be south. The north pole of the bar magnet should be pointing towards south, and south pole should be pointing towards north. So that's how we have to keep it, so that the magnetic field of this bar magnet will cancel BH, right? Option A, right? Shall we move? 54. So before going to 54, I think we need some explanation. Yes, no, it's 52. Yes, we have to go to 54. Yes, this needs some explanation, few more formulas. We will take up, we will group some formulas into small groups, and then we will discuss the questions related to that, because we putting all the things in a group and making it messing up, it's very difficult to understand. Right, any conductor carrying current placed in a magnetic field, we have seen this theory, right? If a conductor carrying current is placed in a magnetic field, it experiences a force as if a charged particle is experiencing a force. If a conductor carrying current I, and if its length is L, is placed in a magnetic field, making an angle theta with the direction of the magnetic field, then I into L cross B, right? ILB sine theta. This is vector. So F is equal to ILB sine theta. If the conductor is placed parallel to the magnetic field, then theta is 0, then force is 0. If it is kept perpendicular to the magnetic field, it experiences maximum force given by Fleming's left-hand rule. If the forefinger, middle finger and thumb are stretched mutually perpendicular to each other, with forefinger showing the direction of the magnetic field, middle finger showing the direction of current through the conductor, then the thumb gives the direction of force acting on the conductor. That you know. As if a charged particle experiences force. That is one thing. And secondly, two conductors carrying current and they experience a force, right? If there are two conductors carrying current, say in the same direction, they attract each other. Two conductors, very long, infinitely long, carrying current in the opposite directions, repel each other. What is the force per unit length acting on each other? Mu naught by 4 pi. 2 IA IB, where IA is the current through the first conductor, IB is the current through the second conductor, and D is the distance between the two conductors by D. And you define 1 ampere using this for the examination. By putting IA IB 1 and distance 1, you get mu naught by 4 pi into 2. So that comes to 2 into 10 to the minus 7. Right? So this answer is not Newton, it is Newton per meter, because this is force per unit length actually. Force per unit length acting on two infinitely long straight conductors separated by a distance of 1 meter kept in air is if 2 into 10 to the minus 7 Newton per meter, then those two conductors must be carrying a current of 1 ampere. So 1 ampere is that steady current flowing through each of two infinitely long straight parallel conductors separated by a distance of 1 meter in air, because it is mu naught, repelling or attracting between them with the force of 2 into 10 to the power minus 7 Newton per meter. And if you want to have the force on the full conductor, multiplied by the length you bring it here. And okay, that is the force between two straight parallel conductors. Right? Now, if you place a loop, current carrying loop, placed in a magnetic field. Suppose this is a magnetic field, this is the principle of the galvanometer. Any current carrying loop placed in a magnetic field experiences a torque, you know it. Suppose this carries a current like this, then these two conductors do not experience any force, this one and this one, because they are along the magnetic field. Either theta is 180 or theta is 0. For this one, theta is 0 along the magnetic field. For this one, theta is 180. So F is equal to BIL sine theta or ILB sine theta. So when theta is 180 and theta is 0, force is 0, no use. Suppose these two conductors are taken. They carry current, one upwards, another downwards. So if you apply Fleming's left-hand rule, magnetic current upwards, magnetic field forward, then the force is inside like this. Here magnetic field forward, current downwards, force outside, so it experiences a torque. What about the force, net force? One force is inside, another force is outside, so net force is 0. Net force on any current carrying loop is 0, but there is a net torque that is given by tau is equal to Bm sin theta, right? Or tau is vector form m cross b. Do you know when a dipole is placed in an electric field, same type of formula. Suppose you have an electric field like this. When a dipole is placed in an electric field, this end experiences a force like this end like this, and if it is a uniform electric field, net torque on the dipole is 0. And if the net torque on the dipole is 0, net force on the dipole is 0, because these are equal and opposite forces, but experiences a net torque. Tau is equal to P sin theta. Remember this? And tau vector is equal to P cross E. Similarly, M cross B. Magnetic moment into strength of the magnetic field. Same two formulas. Now, when does a dipole experience or a current loop experience maximum torque? When theta is 90 degree. Remember, here theta is the angle between the magnetic field and the normal to the coil. It is not the, because magnetic moment is normal to the coil. It is the angle between M and B. So, you have to assume a normal to the coil and magnetic field. This has to be considered. So, angle between the normal to the magnetic field and normal to the coil and magnetic field is theta. So, when the coil is parallel to the magnetic field, and normal is making an angle 90 degree, torque is highest. When the plane of the when the plane of the coil is perpendicular to the magnetic field and normal is making an angle of 90 degree to the magnetic field, highest torque. And when it turns like this, when the plane of the coil is perpendicular to the magnetic field, but its normal is parallel to the magnetic field, theta is 0 or 180, torque is 0. But it never experiences any force. Any closed loop carrying current placed in a magnetic field does not experience any force. Net force is 0, but there is a net torque, Bm sin theta. Now, so if I turn it through an angle theta, I will have to do the work against the torque, because the torque is trying to turn it like this, and if I turn it like this, I have to do the work against that torque. So what is the work done in turning a current loop in a magnetic field? Work done is equal to mb cos theta 1 minus cos theta 2, where theta 1 is the initial position of the angle, theta 2 is the second position of the angle. So work done against a torque in a magnetic field on a current loop is Bm cos theta 1 minus cos theta 2. So when I turn it against the torque and I put it like this, there is an energy stored in the loop, current loop, because it may turn back and it will convert it into rotational kinetic energy. Now, what is the energy stored in a dipole, magnetic loop placed in a magnetic field? Energy stored is minus Bm cos theta. So this is the formula. So all these formulas you have to remember. Torque is Bm sin theta, work done is Bm cos theta 1 minus cos theta 2 from one position to another. Energy stored is minus Bm cos theta, and force acting on a conductor placed in a magnetic field, BIL sin theta. Force between two straight parallel conductors placed in a magnetic field is mu naught by 4 pi 2Ia Ib by d. So all those formulas, very important, but we will see how they are applied in the entrance exam questions. Formulas must be very clear, right? Okay. Shall we move on to a few questions now? Yes, I'm ready. Hope you are also ready, right? Yes. 55. Yes. No, 50, this problem itself is related to that, yes. A wire PQR is bent. A wire PQR is bent as shown in the figure. Which wire? Yes, PQR is here. If you can't see that there, you can see it here. P. This is current carried by it, R. It is kept in a uniform magnetic field B. The length PQ is equal to QR is equal to L. This is L, this is L. the magnitude of the force on PQ and QR will be, and the direction of the magnetic field is given here. Now this part of the conductor, that means everywhere this magnetic field exists, and they have indicated only here. This part of the conductor is along the magnetic field, so force on it is sine 0. F is equal to ILB sine theta. Sine 0, so force on this is 0. What about this part? It is perpendicular to the magnetic field. Sine 91, it is ILB, right? ILB, 0 and ILB. Very easy question, first answer. So that's all. One conductor is parallel to the magnetic field, no force acts on it because theta is 0, and another conductor is perpendicular to the magnetic field. This experiences a force, and if you want to know the direction of force, middle finger upwards, magnetic field forward, force inside. So this conductor, suppose there are two parts of the conductor like this. This conductor does not experience force, this experiences a force and it moves inside because force comes inside part, right? It is like this. Okay, you can follow this Bharatanatyam, right? But you have to do it yourself. Take your hands out and do it yourself, otherwise of no use. Otherwise you have to do only this much in the examination, saying that I don't know the answer, right? You have to do it yourself. Okay, shall we move on? Next problem, very simple one. This one, yeah, it becomes simple only when you know the things behind this. 55. An unsupported horizontal wire, very good problem, is to be prevented from falling under gravity using an external magnetic field. The wire carries a current from north to south. The magnetic field should be directed towards. Wire carries a current from north to south. So we have to hold the forefinger in the north-south direction. So let us make the things easier. Now, the magnetic field should produce a force on the current carrying conductor in such a way that it shouldn't fall. Suppose if I have a conductor carrying current like this, the force on this conductor due to Earth's magnetic field or due to a magnetic field, a new magnetic field, should be such that it should lift it like this. That means it should hold it. The weight acts downwards, but that should be balanced by the magnetic force, the force given by Fleming's left-hand rule. That is force acting on a current carrying conductor placed in a magnetic field. Now we will define the directions first. Suppose this is the surface of the earth, say, and say current is from north to south, right? So better we hold it like this, right? So let this be north, this be south, okay? And north to south, and let this be the other direction, right, like this. When you face towards north, towards your right you have east, right? You have west here. Am I right? So it is like this. I have shown it the board like this. So it is coming out, this is going in. I think you can follow it, right? So north is going like this, and north, from the north you are moving towards south like this, and when I face towards north, towards my right I should have east, towards my left I should have west, right? So I can follow it. You can follow it now. So north, south, east, west. Okay. Now the conductor is carrying a current from north to south. Okay, I will name this. This is the direction of current, north to south. That means our middle finger should be from north to south. Now its weight is acting downwards. You know it, right? mg is acting downwards. That should be controlled by the force acting due to the magnetic field. So that means our thumb should be moving up, correct? Our thumb should be moving up. If the thumb is moving up, did you follow that? So the conductor is carrying current from north to south, middle finger. But our thumb should move up because its weight is acting downwards. It is trying to fall. But the force due to magnetic field should lift it up. So in what direction you have to apply the magnetic field? See, in what direction it is? It is towards east, right? It is coming out. So it should be towards east. Did you follow that? The conductor is trying to fall, but you have to pass a current and apply a magnetic field in such a way that it should be balanced by the weight. The weight should be balanced by the force acting on the conductor due to magnetic field. That is possible when current is from north to south. You can draw the diagram in any way. With respect to this diagram, middle finger should be from north to south, and the force due to magnetic field, thumb, should be upwards. That should be decided already. That means you have to apply the magnetic field in the east direction. It should be towards east. Option fourth one, this one. Okay. So very good problem. Only the thing is you have to do some Bharatanatyam in the examination hall, and you must know the clear idea of the theory. Okay. Yeah, 56. A magnetic needle lying parallel to a magnetic field requires W units of work to turn through 60 degrees. The torque needed to maintain the needle in this position is, okay, how much torque is needed. That means you have to mix up torque as well as work done, right? Both has to be mixed up. A magnetic needle needs a W amount of work done to turn it through 60 degrees. Yes, W units of work done to turn it through 60 degrees. Work done is equal to Bm cos 0, let us start from 0, cos theta 1 minus cos theta 2, right? W is equal to Bm into cos theta 1 minus cos theta 2. Torque needed to maintain this needle in this position, right? Torque tau is equal to Bm into Bm sin theta, right? Sin 60, right? Bm sin 60. Torque needed to maintain the needle in this position. In this position means 60 degrees. Sin Bm sin theta. Bm cos theta 1 minus cos theta 2. Cos theta 1 0. Cos 0 is 1. Cos 60 half. So what is this one? It is Bm by 2, because 1 minus half is half. Bm by 2. Cos 0 is 1. Cos 60 is half. What about this one? Bm sin 60. Sin 60 is root 3 by 2. So Bm sin 60 is Bm root 3 by 2, right? So what is the torque needed? Torque needed, we will divide it. Torque by W, because you see the answers, all the answers are in W, tau and all. So you have to mix it up somehow. So torque by W is equal to Bm gets cancelled. This is root 3 by 2 into this one is half here. So it is root 3. What is tau is equal to root 3 W. Here is the answer. Correct one. Root 3 by W. You can't see that because I have not enlarged it. Because of lack of time, it needs a lot of time to put effort for all these decorations. So I didn't do that. But you have the PDF, right? You see that. Root 3W is the answer. So just see the answers. Torque is given in terms of work done. That means you have to mix it up. Either you have to substitute one in the other, or you have to divide. That is the only option left. So shall we move on? Okay. Next problem. 57. Yeah. Two long parallel straight conductors A and B separated in by 1 meter apart in airs carry currents 1 ampere and 2 amperes respectively in the same direction. A third straight conductor C is placed midway between A and B and parallel to both. It carries a current of 1.5 amperes in the opposite direction. The force per unit length in micrometer or micronewton per meter on C is, right, there are two conductors carrying currents in the same direction like this, and one is carrying a current of 1 ampere, another is carrying a current of 2 amperes. This is A and this is B. Then a third straight conductor is carrying a current in the opposite direction, midway between them, and both carries a current of, in opposite direction 1.5 amperes. Then in the opposite direction, then the force per unit length in micronewton per meter on C is S. What is the force on C? Now these two, and we will take it is as if two charges are kept separated by a certain distance. What is the net force on the charge kept at the center somewhere else, and like that. If this is the center, they are separated by 1 meter, so that means this is 0.5, this is kept at center, this is 0.5, that is given. Now these two conductors should repel each other. So what should be the direction of force on C due to A? What A should do? A should repel C, C should repel A. But what is on C? Question is on C, right? C will repel A will repel C, because they should repel on each other. When the two unlike currents are passing, they should repel. So that means force on C due to A. Force on C due to A. What about force on this is how much ampere? 2 amperes. Yes, that is mistake. I have written simply a 2. Yes. Force on C due to B. It should repel this one like this. Force on C due to B. Now let us see who is the stronger. In that direction the resultant should lie. Okay. Force between any two straight parallel conductor, and they are asking you force per unit length. So mu naught by 4 pi 2I by d. And if it is has to be full force into length you have to do. But here it is force per unit length. Newton per meter. It's a unit. Because it is a force per unit length. Even though I write F, it is force per unit length. Okay, F on C due to A. A is this one. Right? F on C due to B. B is like this. These two now. 10 to the power minus 7. Mu naught is 4 pi into 10 to the power minus 7 divided by 4 pi. 2 IAIB by D. Mu naught by 4 pi 2I by D into, because when you define current, 1 ampere current, you write 2 into 10 to the power minus 7. So 2 IAIB by D. 2 into IAIB 1 into 1.5. 1 into 1.5 divided by D, distance is 0.5. 0.5 can be written as half, right? That 2 goes to the numerator. What is the answer? Force on C due to A is equal to, so this 2 goes to the numerator because 0.5 is half. 4 into 1.5 is 6 into 10 to the power minus 7. And everything is in meters, right? 1 meter ampere, yes. Now, this is towards right. This is towards right. Now, what about the other one? Force on C due to B is equal to mu naught by 4 pi 2 into IAIB 2 into 1.5 again 2 into 1.5 2 IAIB by D again 0.5. Take this 0.5 as half, 2 to the numerator, and it becomes 2 to 2, 8. 8 to 1 and a half, 12. Because 8 ones are 8. Half of 8 is 4. Half, 1 and a half means 8 plus half of 8, 4. That is 12. Right? This is half. 2 here, 2 2s are 4, 4 2s are 8, 8 1 and a half, 12. So force on C due to B is 12 into 10 to the power minus 7. Am I right? 1.5 into 2, yeah, that is 3, 6, 12, 10 to the minus 7. Yes. Now we have to subtract this. Who is stronger? This is stronger, correct? And this is weaker. This is strong, this is weak. Force on C due to A is weak. So where we will write it 12 minus 6 then. So net force on C is 12 minus 6 into 10 to the power minus 7. That is equal to 6 into 10 to the power minus 7. So how much is the answer? Micro, they have asked you to put it in micro Newton per meter. That is 0.6, 1 10 to the minus 7 donated to this. 10 to the power minus 7 and minus 6, sorry, 0.6 into 10 to the power minus 6. And which is stronger? F on C due to B is stronger. So that is the final direction. This is 12, this is 6. So 12 minus 6 towards left, towards A. 0.6 into 10 to the power minus 6 Newton per meter or Newton meter towards A. 0.6 towards A. That is the answer. A. Option A. Right? Okay. We will have up to 16, right? We will finish. 58. Two long parallel wires placed 0.08 meter apart carry currents 3 ampere and 5 ampere in the same direction. The distance between the distance from the conductor carrying larger current where the resultant magnetic field is 0. Okay. You have to find out the point where the resultant field is 0. You have two conductors, two long straight parallel conductors 0.08 meters apart, 3 ampere and 5 ampere carrying current in the same direction, 0.08 meter apart, 0.08 meters apart. And the distance from the conductor carrying larger current where, yes, from some larger current is this one, from this one, the point where the resultant magnetic field is 0. Now where will be the resultant magnetic field 0? First of all, you have to take it very carefully. Suppose you have two charges separated by a certain distance. Where will be the electric field 0? Take a test charge, keep it here. This will repel and this will attract. No, field will not be 0. Take a test charge, keep it here. This will repel and this will attract, right? There can be a field 0 depending on the values. Suppose this is 4 microcoulomb, this is minus 1 microcoulomb. Then this cannot be the position. Why? 4 microcoulomb produces a stronger force of repulsion, minus 1 microcoulomb attracts it with a lesser force of attraction. Cannot be 0. Here this can be the point where net electric field is 0, because minus 1 attracts, plus 4 repels with the same force, because even though distance is more for 4 microcoulomb, it is stronger, minus 1 is weaker, so nearer. So here it can be 0. Similarly, we have discussed that problem earlier already. Similarly here, find out the magnetic field due to these two straight parallel conductors. Then apply the formula. See where the magnetic field is 0. Clasp this with conductor, right? Clasp the conductor with right hand such that the thumb shows the direction of current. Remaining fingers will show the direction of magnetic field. Now, can the magnetic field here be 0? This conductor produces magnetic field outside. This one also produces outside. They will add up. What about here? Can it be 0? This produces inside, 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 inside. This also produces inside. No, cannot be 0 here. It should be 0 somewhere in between here, say. This one produces into the board, right? What about this one? Out of the board. This produces into the board, this one, and this produces out of the board. Can you see that? The magnetic field produced by this conductor, clasp it with right hand, the fingers go in. What about this one? Fingers come out here. Of course, they will be going here, in here, but here they are coming out. So at that point, magnetic field may be 0. Now, let that point be at a distance x from the conductor carrying larger current. Then, let this be 0.08 minus x from here. Now, the magnetic field produced by the first conductor, 1 and 2 I'll write, must be equal to the magnetic field produced by the second conductor. Because they are opposite, somehow we have selected a point where they are opposite. There is no question of again arguing whether they are opposite or not. They are opposite. Only the thing is, even though the two magnetic fields, two vectors are in opposite direction, resultant may not be 0 because they may not be equal. So equal and opposite, that net field will be 0. So if B1 is equal to B2, mu naught by 4 pi 2I by d, you know the formula for magnetic field due to a magnet, 2I by d1 must be equal to mu naught by 4 pi 2I2 by d2. Magnetic field due to a straight conductor at a point very close to it, infinitely long conductor. These are all getting cancelled. I1 by d1 must be equal to I2 by d2. That's all. You see the formula. If more current, more distance. If less current, less distance, so that they are equal. So more, which one? 3 ampere divided by this one, 0.08 minus x, that is equal to, and what is this? 5 ampere divided by x. From here x, here 0.08 minus x. Multiply them, 3x is equal to, this is 0.08 into 5 minus 5x. Bring minus 5x here, what you will get? 8x is equal to 0.4 and x is equal to 0.4 by 8, that is equal to 0.1 times 2 times 0.05 meters from this conductor, 0.05 meters from this conductor and 0.03 meters from this conductor. From the conductor carrying larger current, it should be 0.05. Now, can't you do this in shortcut? Yes, definitely you can do this in shortcut. How? See, mu naught by 4 pi I by d, 2I by d, that should be same, right? If the conductor is having more current, give more distance. How to do that? The conductors are carrying current 3 ampere and 3 ampere. I by d ratio must be same. That means I must be directly proportional to d. Currents are in the ratio 3:5. Distance must also be given 3:5 ratio. What is the total distance? Total ratio 8. Divide this 0.08 into 8 parts. 0.01, 0.01, 0.01, 0.01, 0.01, like that. Give 3 parts to this, 8 parts to this. 8 parts means 3 parts to this, 5 parts to this. 5 parts to this means 0.05. 3 parts to this means 0.03. Directly you will get it. This is 0.05. That's what you can do. As if you do potential problems. If the charge is heavier, make the distance heavier. But in electric field we do if the charge is 4 times more, distance need not be 4 times more, only 2 times more, because in electric field formula 1 by 4 pi epsilon naught q by x square you get. So here we don't have x, d square, here we have only d. So if current is double, distance is also double. So as the currents are, divide the distance in the same ratio. The ratio is 3:5. Total parts is 8. Divide this distance into 8 parts. 3 parts here, 5 parts here. Total it is over. So option B. Shall we move on to 59? We will finish up to 60. Okay. 59. Yes. Here is another problem. Okay. Right. Force per unit length between two straight parallel wires carrying currents in the wires in the circuit is 3.6 into 10 to the power minus 3 Newton per meter. Resistance of the wires circuit is, so this arrangement is like this. Here is a resistor and they want the resistance of the resistor, hoping that these two conductors 1.2 millimeter it's okay, but it doesn't count here. 8 millimeter. Okay, this distance. Internal resistance is 0. It is 18 volt battery. Now these two are very long conductors. Force per unit length between the two long parallel wires, not very long, but force per unit length is given. In the circuit is 3.6. F is equal to 3.6 into 10 to the power minus 3 Newton per meter. Okay, if it is so, we know the formula for force per unit length acting between two straight pair conductors carrying currents I1 and I2, IA, IB are 2, IA, IB by D, because 2 into 10 to the power minus 7 Newton per unit length. Okay, if it is so, IA, IB must be same. Can you tell me why? Because it is a single loop circuit. Whatever current flows through this, same current should flow through this. Current through both the conductors are same. They are separated by this. So they are carrying currents and they should repel each other, because one carries current like this, another like this. And this resistance is, the resistance of the wires are negligible. Now, can I substitute then? 3.6 into 10 to the power minus 3 is equal to mu naught by 4 pi. It is 10 to the power minus 7, this part. 2 I square I will write, this I and this I into I divided by, distance between them is 8 millimeter. Here this one is not of any value, because force per unit length itself is given. I am not multiplying it by L. So force per unit length formula itself. You can find out I. Their question is, what is the resistance of the circuit? Once you get I, V equal to IR, finished. So how to get I now? What is I square is equal to 8 into 3.6 into 10 to the power minus 3 minus 3 minus 6 divided by 8 into 3.6 into 10 to the minus 3 10 to the minus 3 10 to the minus 6 divided by 2 into 10 to the power minus 7. 2 into 10 to the power minus 7. Yeah, 2 4s are. Now if I bring it here, 10 to the power plus 1. So I square is equal to, this is 10 to the power plus 7 minus 6, 10 to the power plus 1. That I will donate it to this. 36 into 4, 4 into 36, finish. That what is I is equal to? This is 6 into 2, that is equal to 12 ampere. I is 12 ampere. Square root of 36, square root of 4. Now apply V is equal to IR. V is equal to IR. That implies 18 is equal to, because there is no internal resistance. Otherwise I would have applied I is equal to E by R plus R. That is not needed now. This internal resistance 0. So I equal to E by R. E is equal to IR. 18 volt is equal to I is 12 into resistance. What is R equal to? 18 by 12. That is 3s are 2s are 1.5 ohm. Oh, here itself. 1.5 ohm. Very. I'm going closer and closer to the same answer. 1.5 ohm. So that is the answer, right? We have in the coming list, we will have one more question of the same type, right? So you can do that yourself, right? Okay, very simple. First of all, you have to use the force per unit length formula and get the current value. Then V equal to IR, right? That's all. One more problem, 60th one. Yeah. A closed loop PQRS carrying a current is placed in a uniform magnetic field. Yes. I'll rub this. Yes. A closed loop carrying a current is placed in a uniform magnetic field. If the magnetic forces on the segment PS, SR and RQ and F1, F2, F3 respectively and are in the plane of the paper and along the directions as shown, the force on the segment QP is, yes. Question is like this. There is a, imagine that the magnetic field is perpendicular to the plane of the board and the conductor is kept like this, and SR and this is PQ. Say the current is somewhat like this and the magnetic field is applied such that force on this is F1 and force on this is F3 and force on the RS segment. Very easy problem. Only the thing is you must understand how it should be cracked down first of all. The question is, what is the force on PQ? And force on PQ should be in some other direction. And also you just now I told the net force on any current loop in a magnetic field should be 0. Net force should be 0. That means if the force on this conductor, suppose the magnetic field is like this, suppose imagine that the force is like this. Net force must be 0. There should be a torque on a current loop. There may be a torque, but there may not be any net force. Net force should be 0. Now, if the net force has to be 0, how come this force in some other direction? This and this has cancelled. What about this one? This and this we can't say it is cancelled because this is longer, this is shorter. So force may not be the same. So what we can say? You split this force into two components, one like this and another like this, right? And if this is theta, randomly I take theta because theta will not have any importance here finally. If that is theta, what is this one? This I will take F4. This is F4 cos theta and this is F4 sin theta. Take the components of this force. Now, if the whole net force acting on the whole loop is 0, then this F4 cos theta must take care of F2, cancel it. What about F4 sin theta? F4 sin theta and F1 when added must be equal to F3, isn't it? Otherwise, how come the net force on the loop is 0? Right? So, the components of this force must take care of all the other forces and must make the resultant 0. So, F4 cos theta must be equal and opposite to F2. What about this one? F4 sin theta plus F1 must be equal to F3. This vector and this vector added must be cancelling this one. Now the net force on the loop is 0. It should be 0. Any current carrying loop placed in a magnetic field will experience net force 0. So now if it is in this form, we won't get what is F4. Net force acting on this PQ will be F4. If I want to get it, I have to make this F4 alone. F4 sin theta is equal to F3 minus F1. And theta is a assumed angle here. Theta has no role here. No answer with the theta. So you have to avoid it. What you can do? You can square these two equations and add it because sin square theta plus cos square theta is 1. So square the equations and add them. So what you will get? F4 square cos square theta plus F4 square sin square theta must be equal to F2 square plus F3 minus F1 whole square. You say you have the options squares. So this one F4 square outside the bracket, cos square theta plus sin square theta here is equal to F2 square plus F3 square, F3 minus F1 whole square. This is 1. F4 square is F4 is equal to root of F2 square plus F3 minus F1 whole square, right? Root of F2 square plus F3 minus F1 whole square. Am I right? Root of F2 square plus F3 minus F1 whole square. That is this option, option D. So idea is to have components of forces. Main theme is net force acting on a current loop is 0. So with this I will stop at once and I will continue in the next class. So you study the other problems in this and you have got the that PDF format so that we can go quicker and you will have higher knowledge if you work out yourself instead of depending on the teacher, right? Hope you will do that. We will meet with more problems in the coming classes. We will gear it up and we will speed it up So hope you will follow me, and you will make the best use of the classes. Thank you for watching the class. Thank you. We will meet in the next class.